Okay, we are on live. We are online. Uh, Welcome everyone. Today, first of all, I want to thank Professor Marat AKHMET from Mathematics Department to accept our invitation. Today, he will give us a seminar about dynamics on label. Thank you, hocam. You can start whenever you feel ready.
Okay. I'm first of all, I'm very thankful for your invitation. It is great pleasure for me to speak on this ODTÜ fizik topluluğu. Çok teşekkür ediyorum. Okay, so I was invited to speak about chaos, but possibly it will be nice to say to be a little bit more useful for you because some elements of chaos you can find some books or videos. But for me, it is important to have this audience and to discuss some my research final last results. And I will speak about dynamics on labels. Türkçe biz bunu anlatsak, bakın işte biz labels'ını etiket diyoruz. O nedenle bu etiket içinde dinamik tip ona bir kabul etsek, bu metot daha bir uygulamaya çok kolay gibi görünüyor. Ben düşünüyorum bu gibi konu size çok enteresan olabilir ve size faydalı olmak çalışırım. Look please that I will demonstrate that the method is universal and we will discuss and consider problems of chaos, randomness, fractals, differential equations, and neural networks. So I will speak in very simple and very picturesque way, such that I suppose that everyone will be satisfied. In my talk, please don't think that some definitions should be given rigorously. Just consider it is like first introduction to chaos theory and to methods which can be applied for the research. So the topic entirely is developed in the framework of our department, mathematical department, with my PhD students, former and present my PhD students. So those who will be interested in the research after this talk, you may find my book published this year in the IOP publishing, that is Institute of Physics. The title of the book is Domain Structured Dynamics. But recently I reconsidered the theory and decided that dynamics on labels is much more suitable and it will be easy to adapt and to understand the theory. In my research, I try to follow, after my research was completed about these dynamics on labels, I discovered that I'm in the flow, which is already directed by for example, this famous physicist Stephen Hawking. You remember his nice research about these black holes and singularity in physics. And he suggested that it is important to explain science not only through equations, but do it through the words and diagrams. And of course, ideally, it is very nice if your research will be rigorously given through words and diagrams. And consequently, I hope that in this my presentation, you will see that about some rigorous things also possible to say, and not through equations, but by using pictures and diagrams, etc. So this is idea of the present talk, one of the ideas of the present talk. Another idea is that, again, it belongs to famous researchers, among them is Ilya Prigozhin, he is a Nobel Prize laureate. And in their books, they suggested to consider a complex behavior which are caused rather not complex systems, but the dynamics of the systems. And again, I discovered that in my research, I can suggest some argument which confirm the opinion of the others, okay? And I will demonstrate to you that complex dynamics can be formatted even in the small number systems. Even I will show to you that 2 points system may express chaotic dynamics. So what I am doing, I can say that it is in the framework of the Pythagoras doctrine. That is, there was a philosopher who in Turkish language it is Pythagore. He lived in the Sisamoda or Susamoda. Okay, and you know this Pythagore or Pythagoras, you know, through the famous theorem of the right triangle. But it is important to remember, and those advanced philosophers or mathematicians, they respect Pythagoras not because of the right triangle theorem. They respect him because of his doctrine that mathematics is universal. And he was one of the first who claimed that mathematics can reflect all the world entirely. For example, misale siz Pisagor söylemiş, biz bu sesini matematik metotlarla araştırma olur mu? Olabilir dedi. Veya ama sesini siz görmezsiniz. Veya ışıklarını, mesela o ışıklarında matematik formüllerle anlatmak olur mu? Ama Pisagor o zamanlarda bir tahmin etti ve çok emin oldu. Bu gibi araştırmalar mümkündü. O nedenle biz bu kişini çok saygılıyoruz. Sebebi Pisagor'un o kadar akıllı oldu, o kadar akıllı güçlü olmuş kişi. And I respect this Pythagoras idea, and let me express to you this idea because it is important for my research comprehension. That Pythagoras says that everything can be expressed through two numbers. And moreover, he says that it is possible to do through natural numbers, or more precisely, even through the finite number digits. For example, from 0 to 9, or even, you remember, this modern time we consider for computers only two numbers, 0 and 1. And everything what can be investigated by computers or reflected through computers can be reflected only through these two digits, 0 and 1. And this is ideas of Pythagoras, which are realized in the modern industry, science, and technology. And what I'm doing with my colleagues, it is exactly as I'm sure that in the doctrine of the philosopher. So let me say to you what we understand as labels. Veya biz onu Türkçe söylesek ne düşünüyoruz? Etiket nasıl, hangi etiketlerini biz kullanıyoruz? We call the set of all labels, we call it as abstract similarity set. And it consists of this type of symbols, okay, some letter, and with indices. These indices are of the final number m numbers from 1, 2, etc. to m. Inside it may be a finite number, not numbers, but symbols. It does not change anything in our research. And each of these type of element we call label, and we use it as for the labeling if we consider some concrete dynamics to be researched. Okay, Bakın işte burada biz onu Türkçe söylesem bu etiket kümesi. Biz etiket kümesinin biz çok iyi bir açıklamalar veriyoruz. Onun içinde bu etiket kümesinde dörtgen gibi veya rektangle'lar anlatıyoruz. Onların bu gibi kümeler. Ve bu kümeler rektangle'lar. These rectangles make some nested sequence. Okay, this infinite nested sequence. Okay, and these rectangles will be also of the use in our next discussion. To demonstrate, to describe these, to visualize these labels, I will recommend to you to consider this Sierpinski carpet. Sierpinski carpet is a fractal, okay, and we call it is like self-similar fractal, and because each part of the fractal is similar to the carpet itself. And by using this small by using the scaling, it is possible to obtain it any small square of the Sierpinski carpet by scaling it, by zooming, if you wish. One can obtain the origin, the entire Sierpinski carpet. And this is exactly rectangles, which I mentioned just in the previous slide, okay? And you can see what we understand is S1 6, for example, S1 7, etc. And we understand also that in that case M is equal to 8 because we have 8 squares for each similar part of the Sierpinski carpet. And if you continue this type construction of the rectangles, that is, you consider smaller and smaller squares, similar parts of the Sierpinski carpet, then the intersection of all of these rectangles make a label which is exactly in the discussion or in the definition have been made in our previous slides. Let me return back, and you can see just if you replace this capital F by the capital S for the Sierpinski carpet, and then you understand that this type of self-similar fractals are very useful to demonstrate these abstract similarity sets. In fact, this idea of self-similarity set, of course, first appeared in our research of fractals, okay, and then we learned that it is possible to extend our concept, our instrument for different areas of mathematics, including randomness we can consider, and we consider also theory of function and theory of chaos and many others. Okay, so another we should introduce in the set of labels mapping, and this that is we introduce abstract similarity map. Abstract similarity map is very simple. We name it as, or we denote it as a phi. Okay, and if the map phi is applied to any element of the set of labels, in that case, result of this applying is again label, but this label is obtained by the previous one just by shifting to the right by one element. For example, if the pre-image started with I1 and I2 is the next one, the next index. In that case, the image is label which started with I2. That is, we just shift and we forget the first index in the mapping procedure. Okay, so this type of similarity map is useful, and it is exactly a proof the name similarity, because if you apply to any rectangle of n order n times, in that case we obtain original label set F. That is, if you, for example, consider the Sierpinski carpet, in that case, if you twice apply the similarity map to the this rectangle S16. In that case, you obtain the original Sierpinski carpet as whole. That is why we exactly very correct to say that it is similarity map, and these self-similarity fractals completely is exemplified what we understand abstract similarity concept. Okay, so possibly it is nice exactly to demonstrate now what we have as a labeling. Labeling, it is, we consider labeling as operator. Okay, but labeling is also can be considered like more visually, like labeling to give some label for each element of dynamics under research or discussion. And veya bakın işe biz onu Türkçe söylesek o zaman da etiket dinamika diyoruz ve etiket kümesi diyoruz. O zaman da çok önemlisi eğer biz bir dinamikle biz araştırsak o zaman da etiketler nasıl kullanıyorlar? Etiketler nasıl biz de etiketlerini yapıştırıyoruz? Bu her elemanlara bu dinamikteki bu elemanlarına. Burası çok önemli ve çok ilginç ama bu başından başlasak biz çok kolay değil. Sebebi biz sonsuz bir büyük bir küme olsa nasıl biz sonsuz etiketlerini bulabiliriz onlar için? Nasıl bu etiketlik yapılır? İyi bir sorular çıkıyor ve buradaki benim amacım sizde birinci anlatmak. Bu nasıl bu labeling, neyse etiket vermek, bu prosedürü nasıl onu biz yaparız. Ondan sonra birkaç örneklerde ben göstereceğim. Burada hiçbir zorluk yok. Gerçekten kolay bir şey yapılır. Ve önceden ben size söyledim, I told to you just before, that our idea is that this labeling procedure is in this dynamics on labeling, it promises to be universal. And I believe that it is similar to that numbers, because of the Pythagoras idea, are very universal to reflect the world. And then we believe that our dynamics on labels is maybe become exactly so much universal to describe chaotic or sophisticated dynamics. Not only sophisticated dynamics. Of course, in that situation, you may say to me, okay, do you believe it is really can be useful and universal in future? Of course, because I know history of the research of science, and then the history says, for example, that this Isaac Newton's invention of the calculus was supported by the research of his teacher Isaac Barrow, who considered this differentiating and integrating geometrically. And then by this knowledge of the results of Isaac Barrow, his students Isaac Newton's invented this calculus, which is rather analytical and formal. But the predecessor was of him, it is Isaac Barrow. And similarly, I strongly believe that what we are suggesting as dynamics on labels may become very universal in future. Of course, it may be some kind transformed. It can be elaborated. The idea is very fruitful. At least in the first hour results, you will see that it is really strong. It is really strong. So here possibly this is why I request a little bit your time, okay, and to express and to demonstrate how the labeling can be done, okay, and should be done if you want to apply these abstract similarity sets for the further research. Look, please, that if you consider some concrete dynamics, it is a triple, which is of the domain, first of all, okay? Then by using this map, and metric. Metric, it is a distance, okay? And for example, if you consider some function, for example, x squared, in that case, domain of the function may be real axis, and x squared, it is psi, it is the map itself, and d, it is Euclidean distance in one-dimensional space, absolute value, okay, which is applied for the 2 points x and y as a distance in the set. And that is why if you want to investigate these dynamics, okay, by labeling, in that case, each point of this f should be given by labels, and these labels can be taken from this set, which I already have shown to you. Okay, we consider, sorry, because this set, okay, capital F, and some element of this set, it is already fixed. Of course, you may choose this m number suitable for you. M may be m small, can be equal to 2, to 3, to 10, or to million. It depends on the situation which you work in, okay? And then by using this labeling, you should assign for each element of this capital F set, you should assign some label, okay? You should assign some label. And this labeling we understand and we denote as a capital L, okay? And we understand it as operator. That is, for each small element f from the set f, we assign label from the calligraph capital F set, okay? And then we say that the result of this labeling, it is result of the application of this operator capital L. Okay, so it is important that to apply our research or this type of chaos investigation in particular, it is important that this map phi, that is abstract similarity map phi, and the specific map psi, which is map of the dynamics under investigation, must agree. Okay, what we understand as a must agree, it means that if you consider that J is an image of the element F by the map psi, in that case, we should consider the image, it is label of the label for the label of the element F, and then the image of the map phi should be labeled for the image of the element F, So that is, if you came to the label in the corner in two ways, then the results should be the same. In other words, what we have that this type of equality should be true for the maps and for the level, for the labeling operator which we introduce. If this type equality is correct, okay, or this type of diagram is correct for the original dynamics and for the dynamics which we call label dynamics. In that case, we should say that this type of maps phi and psi agree with each other. And in further research, we only consider we consider all the dynamics and the labeling dynamics only if the maps agree with each other. And in that case, we say that labeling is possible. And it is important that labeling can be one-to-one or one-to-several. That is, some elements of the capital F set may have several labels, and even then may have infinite many labels. Okay, and it is not important for the future research, and moreover, it is useful if you, for example, consider some random processes. But if the operator of labeling is one-to-one, in that case, we say that we have isometry of the dynamics. That is, this function t, which we use for the abstract similarity dynamics, is isometry. That is, distance between images and pre-images are equal if you consider the dynamics themselves. So this is what we have and what we should say. Of course, it is natural question it is very natural question that if the labeling is possible, this is very important, that how generic the labeling can be. Okay, it is also very important. If there are many dynamics such that this type of methods can be applied. Okay, because labeling, it seems not usual procedure. Labeling something unusual, and this is new, what we introducing in our research. And for example, it is the same like if Pythagoras introduced and suggested in his initial point to apply this type of numbers, and we can, for example, consider decimals, etc., etc. And if decimals can be realized in the world around, or for example, if we have very small in absolute value decimals, it is possible to find some physical phenomenon, some physical objects which can be measured by this type of small numbers. And nowadays, we already absolutely sure that it is possible, that we do not have any doubts. And surprisingly, dynamics on labels the same. Like we have already suggested, we have already discovered that dynamics on labels can be applied to the symbolic dynamics, to the research of the logistic map, and we consider also products of finite number of the logistic map. We consider also famous known Baker's map, or small horseshoes map, and any other hyperbolic sets. Okay, and moreover, we learn that, and I will show to you that this type of dynamics on labels is possible to apply to random processes, to stochastic processes. Okay, that is, despite this, despite of the impression that this dynamics on labels is something artificial, it cannot be applied widely in our research. It is in reality, dynamics on labels can become very universal, okay, and very generic in the research. Okay, and some first steps of the application I will demonstrate in my present talk. Okay, now I want to say about another our achievement, okay, and in research of dynamical systems, and this achievement is related to the Henri Poincaré. This is one of the greatest scientists of the world, okay, and which I really respect, okay, and I try to exactly to be in the research area of this famous French mathematician. By the way, it is of interest for me. It is just because our present talk is some kind of informal, and possibly it is good to say that the date of the birth of the Henri Poincaré, the year of the birth is 1854. And my year of the birth is exactly plus 100. That is 1954. And this is, for me, it is some kind of argument exactly to work in the area which Henri Poincaré worked in. Okay, this is very interesting for me. Okay, so you remember that Henri Poincaré is a famous and great researcher, and he has several, and if not many, achievements in the different areas of mathematics. Famous Poincaré conjecture, which was really solved very recently. Okay, but I must say that for specialists in differential equations in dynamical systems, Henri Poincaré is known for his solution of the three-body problem. That is three-body problem. You remember it is that you may consider, for example, the dynamics, the connected dynamics of the Earth, of the Sun, and of the Moon. We consider these three body, and the question is, it is possible by using this gravitational connection between the bodies and these famous Newton's equations, is it possible to precise dynamics of the three body system? And famous solution of the Poincaré was that he discovered that the dynamics consist of non-closed trajectories. since you are most of you are physicists, students of the physics department, and consequently, it's my pleasure exactly to say about physical problems in my talk. Okay, and it is important for me to say that if you consider this type of oscillations, okay, or recurrence motions. Recurrence motion we understand as a motion which repeatedly the motion returns to some original point, maybe with some not precisely but approximately, okay, to some original point, and that is recursive motions, okay, recurrent motions. And before the Poincare, scientists considered oscillations like which can be presented analytically periodic motions. Okay, and exactly it was Henri Poincare who, because of the research of the three-body problem, who invented these Poisson-stable motions. Okay, a little bit later I will show to you what we understand as the Poisson-stable motions. But for me, it is important that he jumped in his research from the periodic immediately to ultimate type of recurrence is it is Poisson-stable motions. Okay, and those between which you can see in the diagram, that is almost periodic recurrent motions, or we can say also quasi-periodic motion is a part of the almost periodic motion. They were invented later, after the Poisson-stable motions were introduced by Poincare. That is, again, as Henri Poincare jumped in his research a very far, as usually he did in many other his directions of science. It is again one more confirmation how genius this researcher was. Okay, by the way, it is again maybe some of math students maybe listening to me, and in that case I should share some idea. It is not my idea. Specialists in applied mathematics, first of all, there, if you consider this conjunction problem, for example, if you remember that there exist several conjunctions formulated by David Hilbert, and people believe that these conjunctions helped to can have helped to develop mathematics very ahead. But there are specific conjunctions, and Henri Poincare formulated only a single conjunction. But this conjunction was very strong. He told that mathematics should be developed such that application of it to the physical problems must be most productive. And consequently, now we every day in every hour research, we exactly solve the global universal conjunction of the Henri Poincare. And this conjunction is much more useful, in my opinion, of course, for the development of mathematics rather than the specific conjunction of David Hilbert. Okay, this is another interesting idea, and you should understand that in the way of the solution of this conjunction, we have developed mathematics in the application to quantum mechanics, to the different of problems of the liquids dynamics theory, etc., for many and many problems which we have around. Okay, so this is why now it is important that if you look at this diagram, you may find there are a yellow spot. It is unpredictable motion. And this is unpredictable motions. It is our contribution, okay, in to the development of the Poincare theory. And Poincare named these motions like Poisson stable motions after the famous mathematician and physicist of the Poisson. Okay, and we found that in the description of the Poisson stable motion, it is possible to extend it, to develop it to unpredictable motions. And a little bit later, I exactly demonstrate to you how the extension has been made. And consequently, what we should say is that we have introduced this new part, new step in the development of the classical theory of dynamical systems, and exactly in the direction which was shown by the Henri Poincaré. And it is important for us because these unpredictable motions exactly is very nice contribution to the chaos development theory. Why? Because Poincaré himself believes that this type of post-unstable exactly is sufficient for description of the of the irregular motions. But later it was learned that something else should be given, and this something else was done in our research, and I mean this unpredictable dynamics. Okay. So this is just short definition, okay? This is Poisson stability. You can see it was done by Poincaré and George Birkhoff in his famous books of dynamical systems, okay? And the concept of unpredictability was done in our research such that now Poisson stability functions and motions definition was precise by the unpredictability property, and this unpredictability property was exactly given in our research. So for you, I again, as I promised to you, I'm not going to make you boring because of the formulas. I just give this geometrical description, what we understand as a Poisson stability by Poincaré. That is, if you have some initial point, this red point, sorry, because red point, this is initial point of the Poisson stable motion, okay, red point. And then what we have that with the time extension, we have that this trajectory moves, okay, and we have some first ft1p point, that is first point, which return back to the red one. Okay, and then we have another return point, ft2p. It is closer to the red one, and then we have this type of repeating moments. Okay, developing points of the approximation of return. Okay, and they became infinitely. They are infinitely many, and they're closer, arbitrarily close to the original this red point. And this type of dynamics, this type of scenario, if it is possible for the motion, in that case, this motion is called Poisson stable motion. Okay, that is a recurrence. Okay, and this type of recurrence in ideal situations, this recurrence may be, for example, periodic motion, and periodic motion is also Poisson stable. It may be equilibrium. Equilibrium is also Poisson stable, but they are primitive. Non-primitive stability if we have non-closed trajectories, as it is seen in the picture. And the genius of the Poincaré was exactly, he suggested this type non-closed Poisson stable trajectories. And these celestial mechanics, exactly the Earth dynamics or the Sun dynamics, they exactly, how to say, provide these Poisson stable trajectories, non-primitive, which we have non-closed trajectories. Okay, and Poincaré decided that okay, we have this irregularity, and consequently, it is exactly one of the suggestions to say about chaos. But in the time of Poincaré, the chaos word was not known. Okay, just say that it is non-closed trajectories. But nowadays, mathematicians or physicists accept it as a first appearance of chaos dynamics, of chaotic dynamics. Okay, and in my research, little bit, I will say to you in the following sense that Lorentz exactly suggested and proposed to consider sensitivity. A little bit later, I compare these two lines of Poincaré and Lorentz. Okay, and the sensitivity was a new condition for the irregular dynamics. Okay, and then in my research, I tried to derive from the Poisson stability sensitivity condition of the Lorentz. I couldn't, but I couldn't. Okay, and to make this type of intersection of the two lines of Lorentz and Poincare, I introduced a new concept of the unpredictability. It was done together with my students. Okay, more precisely, I did it with my students Mehmet and Urfen. Okay, and this unpredictability is the same trajectory of the boson stability is considered, but you can see that original point, this red point, okay, and if you have approximation this blue point, and for each approximation point, we have that dynamics which started at the two red and blue points, at some moment of time, let's say tau sub n, they diverge, definitely, despite they can be very close, these red and blue points, but definitely they diverge, and this divergence distance is larger than some prescribed point value epsilon 0. And this epsilon 0 should be common for all blue points. And this property, we call it as unpredictability. It is the term, it is name, okay, unpredictability, and believe me that it is deserved to be say unpredictability. Just because of the time, lack of time, I will not, maybe I skip this explanation of the unpredictable, why it is unpredictable, okay. But who knows, maybe it is not our only a single meeting, okay, maybe some I will say to you more, okay. As I told to you, for me it is important in my this talk not to provide to elementary introduction to chaos theory. For me, it is important to say about our results, and I hope that it will be impressive for you, and you will understand through these ultimate results, present results of our research, you will have some knowledge what we understand as a chaos in physics and in mathematics. Okay. Now I will speak to you about two lines, about Poincare line and Lorentz line. And I will speak to you something interesting about the history, how science can be developed. Okay, it is very important. But look, please, that Poincare's suggestion to consider these post-unstable motions as ultimate type of recurrence, and considering this motion in celestial dynamics, okay, and it became a little bit difficult. And consequently, this line of Poincare through recurrence was for some moment of time abandoned. And people started to follow Lorentz line. Lorentz line, it is about sensitivity. That is, Lorentz observed in his numerical analysis of some meteorological problems, he observed that if two trajectories may start it very near to each other, but they necessarily diverge, okay, one and the same number. You can see this type of divergence in my research, but it was done for the same trajectory. But Lorentz considered this type of divergence for different trajectories. It is different than our concept of unpredictability, okay? And this divergence of very near trajectories definitely should be done in future for the trajectories under observation. This divergence was named as a sensitivity by Lorentz. And this concept of sensitivity was and is simple, reliable, easy to apply. And it was like welcomed by researchers, and not only by mathematicians, but many other researchers and engineers are including. And now mostly we have development of chaos theory, and let me immediately say that Lorentz sensitivity is included as a basic element of the Lorentz chaos. Nowadays people say it is chaos just, and we have different types of chaos. For example, we have Lior chaos, we have Divan chaos, okay? But I believe that all of these chaos can be just said like Lorentz chaos, because underneath we have the sensitivity as a basic concept to describe the dynamics, okay? And we say that it is Lorentz line. But then we pay attention, me, myself, with my colleagues, we pay attention to the Poincare line. That is, we follow this Poisson stable dynamics, okay? And we inserted there the concept of unpredictability. And the concept of unpredictability helps us to prove sensitivity in the closure of the unpredictable trajectory. That is, two lines of Poincare and Lorentz line was intersect in our research. Okay, this is very interesting moment. And nowadays we exactly start to work in both, in Poincare line and Lorentz line. And moreover, through our research, we found that Poincare line is useful. Exceptionally, it is useful if one consider probability, random processes, stochastic processes. I will demonstrate a little bit later, okay, if you have some patience. Okay, now very shortly, just why chaos is amusing, why chaos shocked us. For those who are just beginners, or for those who how to say, just want to say what is a chaos is, in that case you remember butterfly effect. That is a small like flapping of the wings of butterfly somewhere in the Texas may cause some tornado and hurricane, and even not in the Brazil, but maybe in Japan, maybe in Turkey. Okay, this is so-called famous butterfly effect. But for the serious dynamicists, we are shocked by the combination of continuous dependence in the initial value and plus sensitivity of Lorentz. And since these both phenomena exist in one and the same dynamical system, it is shocked, because it seems like continuous their exclude that, for example, if you say if you have continuous dependence, there must not be sensitivity. If there is this sensitivity, in that case, there must not be continuous dependence. But they coexist. And why they coexist? How it is possible? It is some interesting research. I will leave it as, if you are curious about this, you can find answer in the definition of chaos theory yourself. Okay, so what is important for the abstract similarity dynamics? How their chaos can be introduced, how inserted, if you wish. For this reason, we formulated two conditions. One condition, we call it is diameter condition, that is diameters of rectangles which were formatted above go to zero if the order of the rectangles goes to infinity. Okay, it is one condition for the diameter condition. So if you remember, if you consider this Sierpinski capit, in that case it is possible to say that diameters of the rectangles exactly is the size of the smaller squares in the Sierpinski capit. Okay, and another property is separation condition. Separation condition, it's here. I do not. Maybe it is seen for you. Okay, that it means that for any small rectangle, doesn't matter if it is. Let me formulate precisely. There exists n, that is degree of the rectangle, and there exists such that for any rectangle of degree n, okay, one can find, and there exists positive number epsilon 0, such that for the any rectangle of degree n, definitely exists another rectangle of the same degree, such that distance between these two rectangles is larger than epsilon 0. And as I told to you, that chaos is created by combination of these two properties, continuous dependence and sensitivity. But in our research of the abstract similarity dynamics, exactly diameter condition is axiom for the continuous dependence, or it is equivalent, if you wish, to continuous dependence, and the separation condition is reason for the sensitivity, or if you wish, it is equivalent to the sensitivity of Lorentz. And consequently, these two diameter and separation conditions, one can accept that it is abstraction. You understand? And this is another reason to say that what we introduce and consider, it is abstract similarity chaos. Okay, because this combination of the two properties exactly makes possible continuous dependence and sensitivity, which we have for classical chaos. But for the, better to say, for the real type of chaos. But we have abstract dynamics, and it is abstract similarity dynamics. And believe me, since I must, sorry, since I must say, sorry, I must say that we are talking about this O2 physics topology, that this abstraction have been made in the framework of our university, my dear colleagues. Okay, and this is important. And by the way, I must say to you that it is my talk, it is simultaneously, it is invitation to join our research. You understand? That by introducing since you are already scientists, okay, now or in future, you must know that if you introduce some nice abstraction, it is start point for the good applications, for the theoretical research. And this formulation of these abstractions, as I talking to you, abstract similarity dynamics, and these abstractions of diameter condition and separation conditions, they may be reason for the further deep and wide research of many and many theoretical problems and applications for the research of real-world problems. So please be aware, and this is why exactly my talk and the subject, the topic of my talk chosen in this case, it is exactly, I follow these my goals, okay, in this talk. Please be aware about this. Okay. So it is important to say that application of these dynamics on labels by the labeling procedure which I have described above to you makes us sure, and we prove it, that domain structuring dynamics or dynamics on labels guarantees all types of chaos. That is Poincare chaos, Lior chaos, Divanu chaos, if the diameter and separation, these abstract conditions, are valid. One more thing, that after we introduce for the Poisson stability this unpredictability property, and then we prove sensitivity, then we are now definitely sure that new type of chaos has been created. And it is our great pleasure and honor that we exactly gave the name of Poincare for the new type of chaos. When we suggested this for publishing for our papers, then editor and reviewers asked us, okay, that you created a new type of chaos, and consequently, you should give a name for this type of new chaos. And then we decided, okay, why not to give the name of Henri Poincare for this new type of chaos? Okay? That is, in this new type of chaos, since now we are talking to the physicists, it was like created the initial point of the chaos is this famous three-body problem in the celestial mechanics. Okay, please be aware about this, that we have this Poincare chaos. And it is pleasure for me to give the Poincare name for this chaos. Why? Because Poincare himself, when he created this, investigated this three-body problem, and he named this special dynamics, he named it as Poisson stable, because Poisson is another French famous mathematician and physicist, okay, and he gave the name of the Poisson for the Poisson stability. And it's pleasure for us to say that this new type of chaos should be named after the Poincare. Okay, this is another thing. Okay, so shortly, if you need definition of Poincare chaos, it is here. It is said that Poincare chaos is that one in the quasi-minimal set with the unpredictability property. If you wish, this is rigorous and short definition what we understand as a Poincare chaos. And it was done in our research. Okay, so now I want to speak about applications. So look, please, that maybe some of our today who are listening to this type of talk, you aware about what is a symbolic dynamics. Okay, what is a symbolic dynamics? And symbolic dynamics is very useful for research. And symbolic dynamics, how to say, it is some kind of very effective instrument for analysis of chaos. For example, if you say that how to prove logistic map, how to find chaos for the small horseshoes or for hyperbolic sets, okay, you will use symbolic dynamics. And it is important for me to say that the symbolic dynamics is just example for our dynamics on labels. You understand? That is, our suggestion, dynamics on labels, much more wide, okay, than symbolic dynamics. And you will see that this type of suggestions makes more easy previous research. For example, if you consider the logistic map, okay, it is just a graph of the logistic function, okay, then let me say to you just shortly that by using escape type algorithm, we proved the chaos, okay, for the logistic map much more shorter than it is done by using symbolic dynamics. Why? Because to prove chaos for the logistic map, we should verify special topological equivalence between the dynamics of the logistic map and the symbolic dynamics. But in our research, by using the dynamics on labels, we do the proof directly. Understand? And the proof of the phenomenon is much more shorter than it is done by symbolic dynamics. Okay? And moreover, we prove unpredictability. That is, we introduce this concept of unpredictability in our research, and we prove unpredictability for the abstract similarity dynamics too. And simultaneously, it means that we prove Poincare chaos for abstract similarity dynamics. If, of course, separation and diameter conditions are correct. And consequently, if you're looking for novelties, in that case, we prove the Poincare chaos for the logistic map dynamics. It is some kind, another beside result, which we have by applying the dynamics on labels. So this is another result, positive things by application of the dynamics on labels. Another interesting moment now we have to say about simplicity. You remember I use this type of words, sentences by Nicolis and Prigozhin. They say that it is of very big interest to consider complex dynamics in simple systems. This is a good example. By using dynamics on labels, we prove chaos for model which consists of two elements. That is, consider metric space which consists of two elements with metric D. Then, by using proper labeling, we approved chaos in the two-element model. But moreover, another interesting thing, that usually our comprehension of the chaos is, if you consider domain of chaos, then domain of chaos also should be complex, sophisticated. For example, something like fractals. If someone remembers this, for example, Lorentz dynamics, you remember this Lorentz chaotic attractor. It is something like butterfly, okay? And it is some kind of rare set, okay? But through our discussion, we prove that chaos is possible even on the cube, okay? Okay, and it is absolutely the cube. You can see that all points of the cube can be and are points of the chaotic dynamics. And consequently, what is the result of our discussion is that we say, by using proper labeling, we may arrange chaotic dynamics for any set. Okay? Of course, it must consist not less than 2 points. For example, for 1 point set, I can't generate chaos. But if the set is larger, it consists of more than 2 sets, in that case, chaos can be arranged. And I hope that this type of results, of course, are important. And I hope this type of results can be applied later, for example, in some computer sciences, etc. Why not? It is some of very, very interesting things which is in the development of our suggestions. Okay. Those who want to understand visually what is a chaos is, just above I consider this domain for chaos a cube, and this is exactly result. This is chaotic trajectory, real chaotic trajectory. And I must say here that these all simulations were done by my former PhD student, Ejeli Ali. He is from Libya, okay, and he is now working at the University of the City Home, okay, in the Libya, and he is very, very skillful and very. You understand that this type of picture simulations exactly helped us to discuss, okay, and we find very interesting phenomenon together with Jelly, and the foundation of this theory was laid in collaboration with Jelly from Libya, by using this our joint research. And this is very nicely done simulation. You can see this is an example of the chaotic trajectory in the cube. And this type of simulation can be done and can be started with any point of the cube, because by the proper labeling. And it is exactly you can say to me, okay, how this labeling can be done? Yes, this labeling was done, okay? And instruments for this labeling already exist. And consequently, now we are absolutely sure that this type of dynamics on labeling, on labels, is useful. Okay, mathematical instruments, mathematical algorithm already exist, and it is very important that nowadays, when computer science is very developed, okay, and it is great, how to say, disappointment for me that we should apply these achievements and this power of computers for many interesting problems. Okay, and it's my pleasure to say to you about this, that I regret about this, that we lose this possibility, that despite the lack of time, we should look for any possibility in the direction and to work, okay? So now I want to say to you about another benefit of application of this dynamic. You can see, for example, usually this chaos was proved for the one-dimensional logistic map, but we can now consider any dimensional
This is
logistic map
the
product.
second
What?
stage of the
Sorry. And moreover, we can also consider perturbed logistic map. And here, for example, you may say that curvilinear fractals, if you wish. Okay, it is also has been done on the basis of our suggestions. And moreover, just maybe shortly.
here one can see
Sorry, it is.
how
You know that it is my
the
former talk, despite I
simplistic triangle
erase.
can be
Sorry.
labeled.
Okay. So this voice must, because I prepared my talk. By the way, this my talk, which I'm now I'm considering for
Using
you.
iteration function
It was done this year in two conferences where I was as a plenary speaker in Portuguese one and in the India, okay, in Hindustan. And now we just a little bit developed to present these our results for today's our talk. Okay, so what more? Another interesting and important part of my speech. That is, if you, as I told to you, there exist two lines of chaos investigation. That is Poincare line and Lorentz line. Most developed and most applied line, it is of Lorentz. But we learned that Poincare line is useful for application, for indication of chaos in ingredients in stochastic dynamics. Okay, and this is exactly preference for the Poincare line. For this reason, I start to consider with my former students, Astrid Tola, he is from Albania, okay, and I started to consider Bernoulli schemes. Simply speaking, Bernoulli schemes, it is like coin tossing. Türkçe biz söylesek bu ne diyoruz? Bakır fırlatma. That is, if you consider coin, it has two sides, okay, head and tail. Or we may say that 0 and 1. And question is, how to investigate these dynamics? Which kind of property for the dynamics can be done, can be investigated? And for example, let me immediately go to some result from the probability theory. We remember that if you say that probability that it is head, it is equal to the half, okay, and this half in probability theory is called like expectation, then if you increase the number of experiments, in that case the relation between appearance of the head to the whole number of experiments goes to the expectation. Okay, for example, if you make this type of 100 tossings, in that case 51 or 49 of head appearance is guaranteed. That is, the relation should be close to 1/2. That's all. For the probability theory, you remember, this is one of the basic results. And if you exclude some more generalization, in that case, you just finalize your research of the coin tossing just by having this type of limit result. But we decided to consider more. We introduced the notion of unpredictable string. What it means? It means that if you put in the row of result of these experiments, that is, if you put, for example, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1. That is, we put the numbers of which appears if you, for example, say that head is 0 and tail is 1. In that case, if you write the result of this tossing, in that case, you obtain this type of sequence consists of 0 and 1. Okay? And you may say that theoretically this sequence is infinite, or it is finite if you stop your experiment by 100 or by 150, etc. And then we gave a new definition. By using this unpredictability concept, we introduce the unpredictability string notion. That is, we say that if the sequence is started with element A0, okay, and we find that for some S, element AS, okay, coincide with this A0, and AS plus 1 coincide with the A1, AS plus 2 the same for A2, AS plus 3 the same as A3, etc., etc. And AS plus K minus 1 is the same as AK minus 1, but AS plus K is different than AK. That is, if AK is equal to 1, in that case, AS plus K is 0. In that case, the string which started with AS and end with AS plus K, we call this string as unpredictable string because it is unpredictable if you compare with the initial string which start with A0. And then question is, what is the distribution of these unpredictable strings? Okay, on the line of all experiments, which is considered as infinite sequence. And we proved that this is exactly shown by this formula. Okay, that is the number of appearance of unpredictable strings which started with element equal to A0 divided by the all experiments number, that is by M. It is again close in probability to the expectation of the element A0. That is, for example, if you consider the coin tossing, and if you consider that A0 is equal to 1, for example, or to 0 as to the head, okay, of the coin. And if you remember that expectation for the head is equal to the half, in that case, the number of the unpredictable strings which started with the head divided by the number of all experiments again satisfies the limit which is on the slide. Okay? What it means? It means that now, my dear colleagues, in our research, we suggest for the classical Bernoulli schemes, for this type of process of coin tossing, which already is forgotten to be researched. Why? Because it is simple and people think that everything already is known for the coin tossing. But we introduce a new concept. And for the classical results, for the classical process, we have new results. That is, in the process which people say it is already have been investigated to the end. It is not possible to do something new there. But we do. We have done. You understand me? And it is important for me to say that biraz Türkçe konuşurum. Bakın işte, değerli arkadaşlarım, inanıyorum ileride belki bu ihtimal teorisine kitaplar yazarken bu üniversite öğrenciler için bu gibi sonuçlar sebebi bu bakır fırlatma, bu klasikal sonuçlar ihtimal teorisinde çok önemli. Özellikle bu öğrencilerle başlangıç bu adım yapan insanlarla ümitim var. Bu gibi bizim sonuçlarımız orada yerleştirebiliriz. Yerleştirebilir. Sebebi biz o kitaplarını yazamazız. Tamam mı? Ama siz fizik öğrencilersiniz. Siz biliyorsunuz bu ihtimal teorinin sonuçları fizikte çok sık sık kullanıyorlar. Çeşitli durumlarda geliyorlar. Gaz teorisini almasanız başka bir teorilerde, başka bir uygulamalarda. Onun için size de umarım bugünkü bu konuşma, bugünkü bu sonuçlar bir neler haberler verdi. İnanıyorum. Tamam. Okay, so now look please at considering this type of unpredictable strings, okay? If you, for example, want to this process to be visualized, I should to say to you that if I consider this type of by horizontal lines for 1 and 0 as a result of tossing, and in that case, by putting that it is a time series, and that, okay, and in that case, you can see that this type of unpredictable strings appearance, it is given by this in red, for example, in that case, you can see that in red, for example, in red, it is exactly presentation of unpredictable strings, which we have introduced by me and my student Astrid Tola. Okay, and it is enlarged a little bit. And this type of unpredictable strings, it is like exactly result of the real experiment, of real numerical simulation. Okay, and by the way, again, what I want to say to you, it is important possibly, that this is good example of unpredictable function. That is, look please, in physics, it is important also to apply nicely developed and defined functions, for example, periodic functions. And we know about the quasi-periodic functions, their oscillations, almost periodic functions. And people also introduce post-unstable functions. And because of our research, we introduce a new type of functions, more sophisticated for the moment. It is unpredictable functions, okay? And we apply these unpredictable functions and we develop its theory. And now we prove theorem about existence and stability of unpredictable functions. That is, this our research, which we have done in the dynamical systems framework, now it is extended and we develop also theory of differential equations by considering new type of oscillations, if you wish. Okay, that is, now everything is connected, interconnected. And this is what we are doing in our research. It is another subject to talk, possibly. I must not too deep there very much. Okay, just I wanted to give some information about this. Okay. So, as I told to you, that it is important for us to say that unpredictability is given in the Bernoulli scheme, that is in the coin tossing. And for example, if you can see here this piecewise constant function, it is unpredictable function, and we prove the theorem, okay, that is in any experiment which we are doing with the coin tossing, always you obtain a part of some unpredictable function. It is general result. Okay, and this general result join the probability, the stochastic dynamics with chaos theory. Okay, because unpredictability, as I told to you, it is ingredient of the Poincare chaos, and consequently we indicated the unpredictability in the stochastic processes, and consequently it is another meeting point of our research. Now, deterministic dynamics meet somehow with the indeterministic processes, with random processes. You remember, we have one meeting point before when Lorentz line has intersected Poincare line. And now what we have? Random processes meet deterministic processes. Okay? This is interesting situation. It is of great pleasure results. Okay? So now what I want
the first
to say to you, this is what we have for differential equations, unpredictable solutions obtained randomly because of this type of, for example, we have not only simply coin tossing, we may consider different models, not only with two finite values, but maybe finite state space we consider it. And another interesting result, Markov chain. Again, I'm not going to give definition of Markov chain. Just since you are physicists, again, you must know this, what is a Markov chain is, or you will know what is a Markov chain. Just remember that in Markov chain, we have found presence of unpredictability. Okay, and moreover, another achievement of our research is modular chaos. And modular chaos, we extended, you know that chaos is considered only for bounded dynamics, but we extended the concept of chaos for unbounded dynamics. And moreover, we combine, we consider it unbounded dynamics, which develops randomly, okay, and found there presence of chaotic ingredients. And then,
since
of
one can
course,
construct
we should consider
unpredictable
application,
functions
okay?
by using deterministic.
Sorry again, because I do not know why in my former presentations is my voice appears. Sorry for this one. Okay, now just simply application. We consider these neural networks, and with my students, my colleagues from Kazakhstan, okay, and one of my former students, Akalbek Jamanchin, now he's in the postdoc and work with me. Okay, we are very intensively and investigate these neural networks and appearance of the Poincare chaos of unpredictability in neural networks. It is another area of the application, and here we have the results, okay, of these applications, and you can see that it is of very interesting dynamics. And this simulation also has been done by Akalbek. I suppose he just hear my talk now, okay, and this is our another
Since
result.
one can
Okay, and if you want to see that the trajectory is chaotic, okay, to that some kind of irregularity to observe, you can see that it is three-dimensional chaotic trajectory, okay, which is at the same time trajectory of unpredictable solution, okay, of unpredictability oscillation. Okay, possibly it is time to stop. Okay, thank you very much.
Teacher, firstly, I want to say thank you about this presentation. It is quite good and satisfactory for me and for, I think, for other people, for watchers. I will invite some questions. Firstly, you generally talk about applications of physics, but what are applications and what kind of application will be created in future? Ya Türkçe söylemek istersen genel fizikteki şeylerden bahsettiniz. Ama ya fizik dışında belli başlı alanlarda kullanılabiliyoruz. Finans veya sizin de içerisinde neuroscience gibi alanlarda. Bunların dışında ileride ne gibi alanlarda kullanılıyor? Bu konu hakkında herhangi bir fikir belirtebiliyor musunuz? Belirtebilir miyiz?
Tamam, çok iyi bir soru. Tamam, çok iyi bir soru. Fizik için uygulamalar değil mi? O sizin sorunuz ne?
Evet. Yani hem ileride fizik için ne gibi kullanılabilir, hem ileride fizik dışı genel olarak şu an kullanılamayan ekstra nasıl bir alanlarda kullanılabilir bu konu?
Biliyor musunuz Yunus? Bu çok fırsatlar var. Anlıyor musunuz? Çok fırsatlar var. Ben size bu genel bir cevap vermek istesem bu gibi söyleyebilirim. Bakın işte oscillation. Oscillation
Evet.
fizik için çok önemli. Doğru mu?
Doğru.
Oscillation'ın varlığın biz onu nasıl biz fizikçilerini biz makalelerini çok okuyorum onu orada mesela hemen periyodlu fonksiyalar veya periyodlu fonksiyalar veya quasi periyodlu fonksiyalar. Biz onun yanına daha bir oscillation'larını dolduruyoruz. Biz onu bu unpredictable oscillation'larını sunuyoruz. Anlıyor musunuz? O zaman da hangi modelini almasan da Duffing equation diye bakın işte biz şimdi arkadaşlarla çeşitli bu elektromanyetik bir cihazların nelerin dinamikini araştırmasını yapıyoruz. Onlarda da biz bu gibi unpredictable oscillation'ın varlığını gösteriyoruz. Tamam mı? O bir. İkinciden biz bu üç body problemine biz bunu baksak o da bir fizik problemi. Doğru mu? Mekanik problemi.
Evet hocam. Evet.
Orada bu biliyorsunuz ve biz ilginç oldu. Biz bu problemini diğerin insanlar hala araştırmamış. Onun için bu problemini de biz yeniden araştırmak başladık. Onun için de unpredictability bakıyoruz. O kadar. Aslında bu sınırsız fırsatlar var. Tamam mı? Sınırsız fırsatlar var. Biz şimdi orada elimiz az. Onu yetmiyor bu problemlerini çözmek. Sebebi nasıl yapmak biliyoruz ama vakitimiz yok ve çalışkan insanlarımız az. O kadar.
Falan da vardı sanırım. Seminer başında siz orada daha çok computer science'e girdiniz ama ya bilgisayarlardan bahsettiniz. Kelimeleri sayılara dönüştürmek. Yine buradan da herhalde sosyal bilimler içinde yeni bir alan çıkabilir. Daha geliştirilebilir bu alanda diye düşünüyorum. Doğru mudur hocam? Demiştiniz ya, you mean worlds can be represented by numbers and computer is a example of this. You say something like that in the start of the presentation.
Yes.
And maybe we can expand this area about by social science. For example, the worlds on the internet, we can try something else, try to build something else. I don't know. Anlatamadım tam olarak söylemek istediğim şey de yani.
Yok.
Yani sosyal bilimlerde de kullanılabilir mi acaba diye bir soru sormak istedim.
Doğru. Aslında yeniden ben Türkçe cevap verebilirim, tamam mı? Durum bu. Bakın işte biz sosyal hareketler en araştırmaya zor. That is most sophisticated dynamics is exactly it is social dynamics. Okay, it is social dynamics, and this is why the more complex, sophisticated functions you suggest, the more useful they will be to investigate sophisticated dynamics. Understand? That is, for example, if you consider, as I told to you, for example, if you consider 17th century or 18th century, people mostly considered periodic dynamics. Okay, periodic motions, strictly periodic, and they were everything else. They just consider it like approximation by periodic dynamics. And then Poincare introduced this Poisson-stable dynamics. Okay, Poisson-stable motions. That is non-close recurrence. Okay, or non-close oscillations, if you wish. And then we started. Mathematicians started to create a new type of oscillations like almost periodic, quasi-periodic, recurrent, etc., etc. And all of them are of use, beneficial for the analysis. And the more complex, the more sophisticated, the better. Okay, but now what we are doing, our unpredictable motions are it is most complex for the present day. Understand? And this is why, if you want to consider sophisticated dynamics, in that case, first your choice should be these unpredictable motions. And this is true also for physics. Okay? And still, what we learned that despite it seems like everything is already done for many parts of the physics, but nevertheless, if you start to think what is a investigation, what is a precise and numerically sometimes results of the analysis, it seems that there are a lot of problems still which are not unsolved and which should be considered. Okay? Which are just maybe described analytically, but if you want to join it is this, which are described numerically, but if you want to impose there something like analytical results, which is some kind of properties which can be seen, can be analyzed, for example, as I told to you in the description of the Poisson stability, or we can, this in the description of unpredictability, we have these sequences of divergence and convergence, then distribution of these time sequences of convergence and divergence. In that case, still there are nice possibilities. That is, what we are suggesting is new properties and instruments for analysis. Okay? To precise what we are having as oscillations, as recurrence. This is what we are doing. Okay? Umarım biraz haber verdim değil mi? Tamam.
Evet. Evet. Tamam, isterseniz bitirelim. Daha fazla soru yok gibi şeyden gelen.
Tamam.
Thank you for your seminar and we will very happy for your heyecanlıyım. Geldiğiniz için teşekkür ederim. Umarım tekrar bir seminer düzenleme fırsatına erişiriz.
Tamam.
Tekrardan görüşmek üzere.
Tamam. Size teşekkür ediyorum. Tamam, görüşürüz. Tamam.
Teşekkür ederim.
Tamam.